Okay, so hello and welcome. We are going to have now the helical springs. So I have sent you a material on the introduction of this one. So I think we have to have a recap on that. We have here the illustration and the parts as well as the labels regarding helical spring. So of course, helical spring are being used in mechanical machines wherein it produces push or pull in a certain surface or in between connections. So helical springs, as we all know, it is formed by a coiled wire on a cylindrical shape. Okay, so it is made up of wire coiled in the form of a helix and are primarily intended for compressive or tensile loads. Okay, spring wire may be circular, square, or rectangular. Basically, you cannot notice what is really the cross section of spring, but the spring may be in a circular, square, or rectangular in cross section. So helical compression springs have applications to resist applied compression forces or in the push mode. So it has stored energy to provide the push. So different forms of compression springs are produced. The helical springs are said to be closely coiled when the spring wire is coiled so close that the plane containing each turn is nearly at the right angles to the axis of the helix, and the wire is subjected to torsion. So the main stress in helical springs are actually twisting. So you expect here some properties like modulus of rigidity as well as inertia. Okay. So the helix angle is very small. It is usually less than 10 degrees. So as we have said, the major stress produced in the helical spring is the shear stress due to twisting. So expect that we will be having here a shear stresses. So the loading applied is parallel to or along the axis of the spring. So I think we are more concerned on what are the formulas involved here. First, we have the spring constant. This is denoted by K, and this is obtained by dividing the loading or the spring load to the deformation of the spring. And it could be related to the rigidity as well as the number of turns of the spring. By the way, the number of turns could be counted here on how many revolutions that these springs are coiled. And of course, there will be a coil angle and then the spring pitch as well as the wire diameter. So we note here that the wire diameter is measured from the outer edge of this wire. And as for the mean diameter, so when we say mean diameter or the capital letter D, it is the diameter formed by the helix out of wrapping in a cylinder. Okay, and it is measured not on the edge but on at the center of this cross section. Okay, so center to center of the cross section, that is the measurement of the mean diameter of the spring. And this is related also to the rigidity, as we are saying, GD4 all over 64 r cube n. So r here is the mean radius, so just half of the mean diameter here, and n is the number of turns. Okay, when we say number of turns, how many turns that this coil is wrapped around along the cylinder. So actually this expression is derived on the deformation of the spring, because the deformation of spring is expressed as a spring deformation delta S or delta spring, which is 64 PR cubed N all over GD4. So here we have also the G, or the modulus of rigidity. So modulus of rigidity, as we have said, it is a property that involves shearing deformation, okay, or a twisting deformation. And then for the stress on the helical spring, it is just the combination of two stresses. So what are those stresses? We have stress due to direct shear on the spring and the torsional effect of the spring, particularly on the spring wire. So that is tau 2. So we have the first stress, the simple formula, shear force all over the area. And then we recall the formula TR all over G for the torsional stress, which involves shearing deformation. So we recall the shortcut formula when we have a solid shaft. That is equivalent to 16T all over pi d cube. Of course, we do not want a spring to have a hollow cross-section. So most of the time it is a solid, and most of the time it is a circular one. So this formula is intended for a circular solid shaft. So we add the two, and then we take note that this T here is in terms of a torque, and a torque is force times a distance, because a torque is a unit for a bending moment force. So in short, we need to express this in terms of force. And what is that? So if we are going to have this illustration here, say this is the wire diameter here, where P is concentrated along that axis. So the distance involved here from the center is the mean radius R. So therefore, our torque is the product of the actual load P times the mean radius. So we're going to replace the T here as P times R, and then V as well, the shear that makes, or the cause of the shear, is actually equal to P also. So we replace V here by P. Okay, so note that area here is in terms of circular cross-section, so we can simplify this as the area of the circular one, of course, that is divided by 4. And then finally, the shear stress in the spring is, we factor out this from these two expressions, and what is left on the first expression is d over 4r, and the second term would be 1. So this is the formula for the shearing stress in the spring. Okay, so a more precise formula that is introduced by A.M. Wall. Let us place it here. To solve for the more precise value of the tau, or the shear stress on the spring. So it is, just copy that one. And then the first term here is 4m minus 1 all over 4m minus 4, which is actually the wall factor, where m is the spring index, equivalent to the mean diameter divided by the wire diameter. So to complete this expression, we must have to add this constant 0.615 divided by m. So this is a more precise formula for the shearing stress at the spring. So AM Wall formula. Okay, so it involves here now spring index. So what is this spring index all about? So it is the correlation between the mean diameter of a spring and the wire diameter of a spring, as we have said. that M is the mean diameter all over the wire diameter. So this proportion will determine the strength of the spring, the stress induced of the spring, and the manufacturability of the spring. So we will discover how to calculate your index mathematically using the spring index formula, how to use the index in the spring design, how to measure a spring in order to determine the index and the most desirable range for spring index to be in. So as we can see, formula is that M is capital letter D divided by the small letter d. So of course we wanted to measure our spring so that we can apply the spring index formula. So as an example, so we have here small index examples and large index examples. So if we notice as we go narrower in terms of the diameter or the mean diameter, the wire should be thickened. Okay, so if we notice here a more mean diameter, there is a small requirement in the spring wire diameter. So as we can see here in the figure, the inner diameter is the inner or the edge here, edge to edge of the inner circle, and then edge to edge or the outer edge of the diameter. Okay, and then the free length is measured as that, and of course the wire diameter, and the count of the coils is just count on one side. So we have a coil number or count here 1, 2, 3, and 4 counts. So revisiting you into the details of spring, of course this is an example of a spring which is resisting a what do we call this, a pull between two edges. So there will be a length, the inside hook. So the inside hook of course has its length, and just the same we will be having a wire diameter here. So this is the cross section. Okay, so the direction of wind is denoted by this illustration. Okay, we have the leg length on both ends or both sides of the spring, and just the same we have the inner diameter and outer diameter, and the number of counts, which is termed as the number of coils. Okay, so let us now proceed to examples so that we can appreciate the formulas and the quantities as well as the given. Say we have the first problem here. Okay, for the first problem, we have a helical spring is made by wrapping wire 25 mm diameter around a forming cylinder that is 175 in diameter. So we consider G, or the modulus of rigidity, to be equal to 82,800 megapascal. So by this, we are going to determine the maximum load possible without exceeding a shearing stress of 140 megapascals. And letter B, the number of turns required to permit a stretch of 100 millimeters at allowable stress level. So first and foremost, we are going to determine what are the formulas involved here. So we have the shearing stress. Of course, the shearing stress is given by this formula, 16 PR all over pi d cubed times 1 plus d over 4r. So we need to know the value of the mean radius r here. No problem with the wire diameter because it's already given. Okay, so the mean diameter is essential here. Anyway, the allowable stress will just be substituted in this equation, and then we come up with the load possible. Okay, the maximum load possible. Okay, so first we illustrate our cylinder. So here is the cylinder, and of course the wire that is wrapped around this cylinder, and the cylinder is noted to be of 175 millimeter diameter. So this is not yet our mean radius. We need to add the wire diameter from the center. So from the center we have that dimension, that small dimension there, and it is actually the half of the wire diameter, that one. And similarly we have for the other side, we have the center, and then we have that dimension, actually that is again half of the wire diameter. So all in all, we can see here that if we're going to add all of this, we can come up with the mean diameter, and that is 175 plus the diameter itself, because half plus half will be a whole diameter. So 175 plus 25 is equal to 200 mm as our mean diameter. So by this we can now proceed with this formula. So allowable here is 140. This one, that is equal to 16p times 100, or half of that 200, all over that denominator, times quantity plus this expression. So if we now notice, the single unknown in the equation is the loading, given that this is 140 megapascals. So P here is equal to 4042.5 Newton. So this is the loading required in order to have, or the maximum loading possible without exceeding our allowable shear stress of 140 megapascals. So next unknown, the number of turns required to permit a stretch of 100 millimeter at allowable stress level. So we take note the allowable stress level, so that is at the level of 140 megapascals. So of course we would want to write the formula that is involving the number of turns and deformation, because a stretch is actually the deformation on the spring, and that is given by the equation 64 PR cubed N all over GD raised to 4. Okay, so the stretch is 100, and then copy the constant here. For the P, we are going to use this one because P, which is 4042.5, is the P at the allowable stress level. So we're going to adopt this. That is placed there, and then the mean radius, that is cube, the number of turns is unknown, all over modulus of rigidity, which is 82,800 times its diameter. Remember that this is a wire diameter, equivalent to 25 raised to 4. Okay, so this is the equation. We solve for N. N is found to be 12.5 turns. Okay, so this is for the first problem. Moving on to the next problem, we have, okay, so here's the problem. We have here a rigid plate of negligible mass rests on the central spring, the figure. So it is 20 millimeter higher than the same symmetrically loaded outer spring. So these are the outer spring, and it is 20 mm short on the plate. Okay, so each outer spring, of course, there are properties of the outer spring. Wherein 18 here is the N, 10 millimeter diameter is the wire diameter on the outer spring, and the mean diameter is 100 millimeter. So the central spring has also its properties, where in N is 24 turns, and the diameter of the wire is 10 millimeter. The mean diameter is 150, and then the modulus of rigidity is 83 gigapascal. So the load P will be applied on the center of the plate. We are going to compute the load carried by the central spring, the maximum shearing stress on the central spring, and the maximum shearing stress on the outer spring. So there will be 3 unknowns here. Of course, the approach actually is similar to problems of thermal stress, axial deformation, torsional stress, because the concept here is just to utilize the free body diagram and then work with the geometry. What can we derive out of the geometry regarding the deformation and the loading? So starting with the loading, of course, if we load this one, this external spring will be now involved in carrying this platform, although they are short of 20 millimeter diameter. When this is loaded, it will involve them in carrying this platform. So we are going to place now the loading, and that is 5 kilonewton. And we wanted to bring this platform downwards as to indicate our deformation. So this outer spring will have its deformation. Say I'll indicate that as delta O. So this will be the length that is being pushed by this platform up to this extent. Similarly, the central spring would also have its deformation. See, I'll just denote that by delta inner. Okay, so delta inner for the central spring and delta outer for these two identical spring here. So we would also like to denote or place here the gap. So that is 20 millimeter gap. And of course, we can now clearly see what equation we can form out of this geometry. So we can say by deformation, we have the inner deformation will be equal to the outer plus 20. So substituting each of the delta here, you'll be having the formula. Of course, we have 64 PR cube N all over GD4 for the inner spring is equal to 64 PR cube N all over GD raised to 4 for the outer spring. Of course, we place the remaining term there. Okay, so by this, we can now substitute all of the properties. We have 64, that is the inner loading. The mean radius is 75 for the inner, and that is cube. And then for the number of turns, we have 24. So we divide this by its modulus of rigidity and the diameter, or the wire diameter, which is actually 20. Okay, so let us check on that. The inner spring. Okay, so here it is. It refers to the central spring as 24 turns of 10 millimeter diameter wire. Okay, so I think we should correct this given. This is supposed to be, okay, so this is supposed to be 20 millimeter, and then 24 turns are, or all are reflected here. Okay, so we move on to the other side of the equation. We have the constant, the outer force of the spring, or the outer spring force, PO. The mean radius is the half of 100, that is 50, and that is cube, times the number of turns for the outer spring, 18. Of course, we divide this by the same material, this 83,000. So the diameter is smaller, 10, and then that is raised to 4. We just add 20 there. Okay, so if we notice, we will be having a relationship between the inner loading and the outer loading, or the spring inner and the spring outer loadings. So we simplify the equation. That is 0.048 pi is equal to this constant, that is 0.1734 PO, and we maintain the 20 there, the last term. So we label this as equation 1. And as usual, this equation 1 would be supplemented by the equation from your free body diagram. We illustrate the platform, and then the loading, and then the reaction from the spring, which is 2 loading from the outer spring and 1 for the central spring. So obviously, we'll just have to take equilibrium equation along the y-axis, and then we can say that Pi plus 2PO is equal to 5. So let this be our equation 2. Okay, so we have equation 1 and equation 2. I think this should be arranged according to the same or organized variable and constant at the right side. So we'll just arrange this one into this equation. So the same arrangement, constant are at the right side now with this 1 and 2. We will calculate the two variables, and the values are 3,367.35 Newton for the inner spring, and the outer spring loading is 816.33 Newton. So as we have said, the procedure on the previous topics are just similar, only that the formula for deformation is on the spring. So these are the loadings derived, and the stress will follow. Okay, actually this is the first unknown, and the other unknown would be the maximum shearing stress on the central spring as well as the outer spring. So we'll just have to substitute values here from the formula. We erase that first. For inner spring, we have this one. Of course, this is exclusive for the inner spring. So we substitute all of the values. So here it is. Just adapted this P here, and then just substitute the mean radius as well as the wire diameter. So we come up with 171.49 megapascals. And as for the outer spring, we'll do the same. Of course, this is for the outer spring, and then Again, we substitute the values. So here again, we adopt the computed value for the PO, 816.33, 816.33, and then substitute all the mean radius as well as the wire diameter. We come up with 218.27 megapascal. So this is for the second problem.